So we said that we could look at a common ion affecting the solubility of a sparingly soluble salt. Right? It's going to work by Le Chatelier's principle. So if I add the common ion, it's going to move it back to the left. Equilibrium will shift to the left, whether I've added calcium or whether I add fluoride. For things that are going to be tied into pH, it's going to be a little bit more interesting, like magnesium hydroxide, not terribly soluble, iron hydroxide, not soluble, but I can change their solubility around by playing with the pH of a solution. If I've got high pH, I've got a lot of hydroxides, that's going to act to shift the equilibrium to the left, because it's like adding a product. If I've got a low pH, it's like removing some of my product. Equilibrium is going to shift to the right and make it more soluble, so I can help dissolve magnesium hydroxide in water, right, by changing the pH. Right? So here's another example of the common ion effect just in a picture. So I've got sodium fluoride added to the system of calcium fluoride. The sodium is not going to change this at all. It's not showing up in the equilibrium expression what the fluoride is. So as I add more and more sodium fluoride to my calcium fluoride solubility is going to decrease as I add more and more sodium fluoride. Let's look at an example of how we would do a calculation with that. So let's calculate the solubility of magnesium fluoride in 0.1 molar sodium fluoride. So I'm going to set it up. Here is my balanced chemical equation. I would set up an ice table. I'm going to skip to the equilibrium line where I've got x, and that's going to be plus 2x, but I've started off with 0.1 molar fluoride to begin with. My KSP is 7.4 times 10 to the minus 11, which is equal to Mg2 plus times F minus squared, so x times 0.1 plus 2x squared. We're going to assume that this x is small. Again, you do not have to. You can have your calculator solve that if you'd like. It's just going to get a little bit hairier to do that. So I get K is equal to X times 0.1 squared. So my molar solubility is going to be 7.4 divided by 0.1 squared, or 7.4 times 10 to the minus 9. Well, let's do another example. Calculate the molar solubility in the presence of a common ion. So we're going to calculate the molar solubility of barium sulfide in the presence of 0.01 molar sodium sulfide. So we'll set up our balanced chemical equation, set up our ice table. We've got no barium to start, so our initial concentration is 0 for the barium and 0.001 for the sulfate. We're going to gain a little bit of barium. We're going to gain a little bit of sulfite. This is a 1-to-1 stoichiometry, so it's S and S here. So our equilibrium concentrations are S and 0.001 plus S. Set up the equilibrium K line. K is equal to barium concentration times sulfide concentration, which is equal to 1.1 times 10 to the minus 10. Or S times 0.001 plus S, which is about equal to S times 0.001, is equal to 1.1 times 10 to the minus 10. Rearrange and solve for S. You're basically just going to divide this by K, or KSP, by the concentration of the common ion, and we end up with 1.1 times 10 to the minus 7 molar. Here's another example. I've got calcium fluoride, and its KSP is CaF squared. What if I've got an initial 0.1 molar fluoride ion concentration? Well, set up my equilibrium tables. This is my initial concentration of fluoride. Nothing for calcium. Gain a little bit of calcium. Gain 2 little bits of fluoride. So S and 0.1 plus 2S. KSP is calcium 2 plus times fluoride minus squared, or S times 0.1 plus 2S squared. S is small, so S times 0.1 is KSP. Rearrange to solve for S, and we get 1.46 times 10 to the minus 8. For comparison, in pure water, it's 3.32 times 10 to the minus 4, so that the calcium fluoride is 20,000 times more soluble in water than in the solution of sodium fluoride. So for insoluble ionic hydroxides, the higher the pH, the lower the solubility of the ionic hydroxide. And the lower the pH, the higher the solubility. So this is our effective pH. The higher the pH, it means increased hydroxide ion concentration. And if this is our generic chemical equation, adding hydroxide at a high pH means I'm going to shift that to the left. For anions of a weak acid, the lower the pH, the higher the solubility. So I've got something like M carbonate, right, which is going to dissociate into M and N CO3 2 minuses. Well, this carbonate can react with H plus to form HCO3, right? So it's going to remove this product, and it's going to form HCO3 and water. Again, that's just Le Chatelier's principle at work. So if I've got our calcium fluoride dissociating to calcium 2 plus and 2 F minuses, if I can remove some of this F minus, the equilibrium is going to shift towards the product, causing more calcium fluoride to dissolve. So F minus can be removed by adding a strong acid. F minus plus H plus gives me HF. As the pH decreases, the H plus ion concentration increases and the solubility increases. So the effect of solubility on pH can really be dramatic. So for this particular reaction, as I go from 7 to 5 to 3, and then I start getting down to 2 or 1, right? So because remember, HF by itself is going to be somewhere around in here. Right? So you're going to start making the HF somewhere around pH 3. As I drop my pH and I get more and more H+, my solubility just shoots up. Right? So this is in the molar solubility in terms of per moles per liter, and I can double or triple or quintuple my concentration in solution just by changing the pH. So determine whether each compound is more soluble in acidic solution than in a neutral solution. That's an example. So I've got barium fluoride, silver iodide, calcium hydroxide. All right, so barium fluoride is going to be more soluble in acidic solution because the way we pull away the F minus, which is a weak base, is to react it with a strong acid, H3O plus, low pH, put it in acidic solution. I get rid of some of my F minuses. That's going to allow more barium fluoride to dissociate. AgI, that guy is not going to be greater in acidic solution because this I minus is not a base because it's from the conjugate of HI, which is a strong acid. And if this had been Ag acetate, right, then I might be able to change the pH. Calcium hydroxide, right? Well, the calcium hydroxide is going to be more soluble in an acidic solution because I'm going to pull away the OH minuses. I'm going to react that base part with the H plus to form water, which frees up more room for this calcium to dissociate. This is a terribly worded question down here. Why? Because you can't directly compare these two. And I think what they want to say is if I take PBBr and I put it in an acid, is relative to the aqueous solution. So this is not going to, because the Br is not going to be pH dependent. This carbonate will have a strong effect with pH. All right, precipitation. We said occurs when Q is going to be compared to K, and we can call that saturated or not saturated. So if Q is equal to K, it's saturated, no precipitation occurs. If Q is less than K, the solution is unsaturated, no precipitation occurs. If Q is bigger than K, I got more products than I should have. K is the system is going to move to relieve that stress. It's going to precipitate until the concentration drops. Some solutions with Q bigger than K will not precipitate because they are supersaturated solutions. Because we can do this, right? Based on the solubilities of things, we can selectively remove ions from by precipitating them out of solution. So if I've got a mixture of zinc and copper, the copper has a KSP of 6 times 10 to the minus 37, and that's less soluble than the zinc sulfide, which is KSP of 2 times 10 to the minus 25. The copper will be removed from the solution or precipitate out of solution before the zinc. Right? It is less soluble than the zinc, so we can do selective precipitation by adding H2S. It's added to the green solution. Black copper sulfide is going to form in a colorless solution of zinc plus. If I keep adding in H2S, then a second precipitate of white zinc sulfide forms. So this lets us separate ions based on their salt solubility. So if HCl is added to a solution containing silver and copper, I'm going to form copper chloride. AgCl's got a precipitate of it's going to precipitate out when the concentration is the square root of 1.8 times 10 to the minus 10. It's about 1 times 10 to the minus 5 molar. So not very much HCl needs to be added to precipitate out the silver chloride, but the copper is going to remain in solution. That removal of one ion from a solution is called selective precipitation. Right. So it's going to happen if Q is bigger than K. So I can add in some common ion here. Right. So I've got AgNO3. I'm going to add in the add in the sodium chromate and form silver chromate. Or if I can precipitate it out if I've got a supersaturated solution, and the supersaturated solution is going to precipitate out until I reach the regular saturation conditions and I reach K. It's often the case that we can prepare aqueous solutions of two ionic compounds that are very soluble, but we may be able to make ion pairs to make a compound with a much lower solubility. So, example, silver chromate is going to dissociate into Ag plus and chromate. With the Q, we're going to check the Q. If we're going to keep adding sodium chromate and AgNO3 will eventually have Q is bigger than K, and silver chromate will precipitate. Here's another example. And sodium bromide, and we're going to form, the solution is going to have 0.01 molar lead nitrate and 0.0035 molar sodium bromide. Does it precipitate form in the newly mixed solution? Well, we know on a gut level that silver bromide should precipitate. It's not going to be soluble. The sodium and the nitrate, right, this isn't always going to be soluble, and the nitrate is always going to be soluble, so we don't need to worry about those, just the potentially insoluble compound. First thing we need to do is this is a Q compared to K problem, right? So the sodium nitrate is always soluble. The lead bromide has a KSP of 4.6 times 10 to the minus 6. Let's check our Q. Q is the lead concentration times the bromide ion concentration squared, or 0.015 times 0.0035 squared, 1.84 times 10 to the minus 7. Q is less than K, no precipitate forms. And so this is called fractional precipitation, the separation of ions based on differences in their solubility, and you choose the proper reagent to bring about precipitation. And it's all based on KSP values. For example, we can separate Cl- and Br- using silver nitrate because the bromide is much less soluble than the chloride is. So, for example, lead-2 nitrate is added slowly to a solution that is 0.2 molar in chloride ions. Calculate the concentration of lead ions required to initiate precipitation of the lead chloride. The KSP for lead is 2.4 times 10 to the minus 4. Start off with our balanced chemical equation. And set up a K expression. We want to figure out when it's going to precipitate. It's going to precipitate when, so we're going to take our K over here and we're going to divide 0.02, because that 0.02 was our concentration of chloride ions, because we're adding in the lead nitrate. We're going to find out how much lead nitrate we need to add. So our chloride concentration was 0.02. Rearrange this to solve for lead, so 0.6. So concentration of greater than 0.6 molar will induce precipitation of the lead chloride. So you can add a couple of drops until you reach 0.6, then you start to form a precipitate. It's fairly high because lead is reasonably soluble.